Good morning, or I suppose afternoon, everybody. Good morning or afternoon, depending on when you're watching this. I hope you are having a good day. This is going to be my lecture on heat and temperature and thermal energy. I might recap some of this stuff when I'm back in the classroom later this week, because this is stuff that I prefer to, do more in person. But I can do an initial one here. So, I want to talk to you about thermal energy and all of the concepts that are related to that. Thermal energy is the energy that really, comes to be associated with things that we think of as thermal. Heat, temperature, and all things related to that. But the basics, right, of thermal energy, it isn't defined by any of those. It's defined by the energy of the constant random motion of atoms and molecules. So if you guys remember when I talked about the solids staying in place and vibrating, right, and the liquids moving around each other, and the gases going everywhere. Well, that is thermal energy. Sorry, I had to bump my camera there. That is thermal energy, the energy of that motion. So, heat has a lot to do with that. But before we talk about heat, I also want to talk about temperature. Temperature is a measure of an amount of thermal energy in a substance. It doesn't directly tell you the energy. Rather, we've discovered a scale that can give us comparatively different amounts of energy, or different temperatures, showing different amounts of energy that we can convert to actual units of energy, like the joules that we covered last time. So a hotter object is hot because it has more random motion in its atoms and molecules. It has a high temperature because the temperature is measuring all of those random movements. And it's not the direct amount of energy. It's more that it's related to the direct amount of energy. My apologies. I'm very tired right now. It's almost midnight that I'm finishing recording this. So, I want to talk about heat. Heat is a weird concept to understand. But I want you to think for a moment about experiencing heat or experiencing cold. Now, experiencing something hot or something cold, in terms of chemistry, are both instances of heat. Heat is energy. Well, specifically, the transfer of energy. This might sound a little weird, but every time you experience heat, right, we're experiencing heat when we experience energy transferring into us. And we only experience cold when we experience energy transferring out of us, which itself is still heat. So again, think about it this way. You could do a little experiment at home. Stick your hand in the freezer for 30 seconds and shake your brother or sister or parent's hand. You will feel warmth. You'll feel cold from the freezer. you'll feel cold from the freezer because your energy is being transferred into the freezer, leaving you with less. But then, when you go and shake hands, you will experience shaking hands as warm, and they will experience shaking hands as cold. Because you are transferring your energy, or they are transferring their energy. My apologies. To you. If they're transferring their energy to you, that is heat. Heat is the transfer of energy. So whenever you feel something that is cold, that is still heat in the chemistry sense, in the sense that it is energy being transferred. Temperature and heat are not the same, right? Temperature is a measure, but heat is an exchange of energy. So if you put cold ice in a bucket or a cup of warm water, energy would transfer from the warmer water to the colder ice. That is heat. The temperature overall, or I'll say the temperature of the water, will go down. That is a measure of the amount of thermal energy, not the exchange. The amount of thermal energy in the water has gone down because it went into the ice to cause the ice to melt. As far as temperature goes, we have a few different temperature scales. We have the Fahrenheit scale, in which 0 degrees Fahrenheit is the freezing point of a concentrated saline solution, aka a salt water solution, where the normal body temperature is around 96 degrees. A lot of people say that Fahrenheit is arbitrary compared to Celsius, because Celsius has water freezing at 0 and water boiling at 100. Well, truth be told, these are invented scales. They are all arbitrary. Right? We're just making the decision there to base Celsius off of 0 or off of water. Right? Water is an important chemical, but it's also just another chemical. So that's a pretty arbitrary choice. Instead, we'll be talking about Kelvin mostly. Interestingly enough, though, for Fahrenheit, the guy who invented it was brilliant. His name was Fahrenheit, and he invented Fahrenheit thermometers, which people started using because they were so accurate. However, he was very protective of his work, and he never told anybody what he actually based his scale off of in order to get his extreme levels of accuracy. Some people have, believe that it might have something to do with mercury, though. So, truth be told, Fahrenheit is actually based off of something. Being at 100, we don't know what it is because the guy wouldn't tell anybody, and then he died. Celsius goes from 0 to 100. Room temperature for Celsius is around 22 up to 25 degrees Celsius. However, Celsius still has issues in chemistry. Namely, it is possible to have negative numbers. We like to avoid negative numbers because negative numbers can throw off a lot of our calculations. Instead, we avoid that using what we call the Kelvin scale. The Kelvin scale takes the coldest possible temperature, 0 Kelvin, aka absolute zero. At absolute zero, there is no thermal energy. So absolute zero is negative 273.15 degrees Celsius, approximately. And to make things simple for us, we actually base Kelvin off of Celsius. Going up 1 degree Celsius will also go up 1 Kelvin. Instead, Kelvin is always 273.15, or we usually round to 273, greater than Celsius. Here we can see 0 and 100, and then 273 and 373. Room temperature being about 295, aka 22. Fahrenheit is 5/9 the size of a Celsius degree, and a Celsius degree and Kelvin are the same size. I shouldn't have said Kelvin degree, as Kelvins don't have degrees. I will correct that. In fact, I will correct that right now. And I'll do uppercase 2, Kelvin, are the same size. There we go. Okay, you should know this formula. To go from Kelvin, or to go from Celsius to Kelvin, just add 273.15. And to go from Fahrenheit to Celsius, you should subtract 32 and divide by 1.8. Dividing something by 1.8 is the same as multiplying it, right, by 5/9. So you can do Fahrenheit minus 32 times 5/9. Let me check my time real quick. I might do somewhat of a short video and pair it with some problems as it's late and I hear a sad baby. Alright. So I just want to talk about heat capacity really quickly. Heat capacity is the amount of heat required to change the temperature of a substance by 1 degree Celsius. You'll remember that's very similar to the definition of a calorie, right? The amount of heat required to change the temperature of water, 1 gram of it, by 1 degree Celsius. That is because the word calorie comes from something called calorimetry, which I'll actually be getting into in a minute. And calorimetry uses the heat capacity, so they are completely related. Basically, every chemical has a different heat capacity. It is a property of that chemical, a physical property. Water's is 4.184 joules, which, if you remember, 1 calorie is 4.184 joules. So again, not an accident, right? It is the same number as the heat capacity. However, every chemical has a different heat capacity. some things have low heat capacities. I'm trying to remember how many slides so, for example, metals. Let's think about what that means for a second. The amount of heat required to change the temperature by 1 degree Celsius. So if the heat capacity is low, that means it actually doesn't take a lot of heat, it doesn't take a lot of energy to raise its temperature. Metals. Metals have low heat capacities, right? Because it doesn't take long for a metal to heat up. Think about this. You can put a pot on the stove. That pot, we know, is too hot to touch. And a lot of these things, right, we have this knowledge in our head, and we just don't put together the reason why, right, the chemistry. And so part of being a good chemist is seeing these things that we just take for granted out of the universe and asking why. So you know that the stove is hot, but you know that if you're heating up water on the stove, it will take a while for it to get too hot to touch. You might even test the temperature of a soup you're heating up with your pinky, right? Or dip a spoon in and put it right in your mouth. Despite the fact that you wouldn't touch the pot, because you know that would burn you, you'll put the liquid in the pot in your mouth immediately, because you know it won't, because they have different heat capacities. So the heat capacity of the metal in that pot is really low. So let's just imagine an amount of heat. So let's just say 100, right? You know, this isn't a real amount that would do anything, but 100 heats, right, go into the pot. It makes the pot really hot. That same 100 heats goes into the water. It makes the water warm. Water has high heat capacity, and so it takes more heat to raise the temperature. The pot is a metal which has a low heat capacity, so it does not take much heat to raise the temperature. Right? That's why you'll also get different temperatures for, let's say, playground equipment. Right? I'm sure you guys remember your playground days. You know that, well, a plastic slide that's been out in the sun all day will be pretty hot. You definitely don't want to go and touch the metal slide that has been out in the sun all day, because the metal has a low heat capacity. It's going to heat up much faster and get much, much hotter than a plastic slide. Or go and touch a car on a really hot day. It's going to hurt if you go and touch the hood of the car, because again, it has been heating up all day. So insulators, heat insulators, are things that have a high specific heat capacity. Think about a mug, right, that you might have that doesn't feel hot even when you put boiling things in it. That's because it has a high heat capacity, right, and it stops the heat from moving. So I'm actually going to put forward an idea to you, and I want you guys to think about it and maybe have a discussion about it in class. I will tell Miss Gendro the answer. Please don't look it up, because honestly, it's a worthwhile discussion. There are only 2 states in the United States of America that have never had a temperature above 100 degrees. The first one is Alaska, because it's cold. But the second one does not have to do with cold. It has to do with heat capacity. It has a high amount of something that has a decently large heat capacity. Right? It is surrounded by this heat capacity, it is surrounded by this substance with a high heat capacity that stops it from getting warm. So I want you to think about what state that might be, and Miss Chandra will have the answer. But here are some heat capacities to look at. Metals are really, really small. 0.128 lead and gold, 0.235 silver, right? 0.385, 0.449. Then you get up to water. Water's 4.184. So think about this. You put the same amount of heat into iron and water increases its temperature 10 times as fast. I know I said have this data table is needed when solving homework problems. This data table is needed if you're solving homework problems where I give you these. To be honest, most of the time I actually just give the numbers with the problem, but if I don't, you just refer to it here. So I mentioned, let me do a real quick check of the time. Okay, I'll do this real quick. I mentioned calorimetry a few minutes ago in relation to calories, but what actually is calorimetry? Well, calorimetry is a measure of the amount of heat being absorbed by a process. This is how we calculate calories. Generally, calorimetry is done by heating something up, often by burning it, or having some sort of chemical reaction that's producing heat. From here, right, we measure the temperature change of something to calculate the amount of heat that is being transferred. This is usually done through burning. In fact, this is actually how we get calories for food. If you have, let's say, a Cheeto, that Cheeto has a certain amount of energy stored in it, in its chemical composition. It is chemical energy. Right, we talked just the last class, or 2 classes ago, about the stability of a bond and its relation to chemical energy. And so if this bond is really stable and has a high kinetic energy, or sorry, has a high chemical energy, right, when our body breaks it down and digests it, it breaks up those bonds and it takes all of that chemical energy and it can use it to fuel us. Well, those same chemical energies are released when they're being burned. And so you can approximate how many calories a food has by burning it. And in fact, advanced calorimeters are exactly how we get those numbers. We could do calorimetry simply by burning something in, over a soda can, or doing a reaction in a cup of water. Right, but more advanced calorimetry is often done with something called a bomb calorimeter. So right here we see heat is equal to the mass of our chemical times the chemical's specific heat times the temperature change. You could do something like this just to figure out, like, okay, you have a hunk of metal. You know that metal's specific heat. You know how heavy it is. You measure its temperature change. You could say, well, how much heat is required for that? You could do something similar where you could say, okay, how much heat is required to heat an entire Olympic swimming pool, right? Up from 20 degrees, up from 5 degrees Celsius to 50 degrees Celsius. And you could get a heat, right? And you could get that in calories, which means you could calculate how many cheeseburgers it would take to burn, approximately, if they were burned efficiently, to raise that temperature of the pool. Delta, the triangle, is a symbol that we have in chemistry that means change. In chemistry and physics and science in general, delta usually means change. Most of the time, this is done with water. Even if you're burning something, usually, again, I would burn a Cheeto right underneath a can of water. I would measure the mass of the water, and I would measure the temperature of the water as it changes. Then, right, I would have my specific heat capacity of my water, 4.184, and I could figure out how much heat and how many calories. Water is a really easy one to use, and one of the reasons we use it is instead of trying to figure out the specific heat capacity of every obscure random chemical, right, what's the point in that when we can figure out, when we know the specific heat capacity of water, and can just burn it? Because there's plenty of chemicals we don't know the specific heat capacity for. Somebody has to go and discover that, and it might not be worth our time if we can just relate it to water instead. So here would be a quick example of that. All right, you guys can pause these two slides and look at it. It's basically finding the amount of heat. It gives an initial temperature and a final temperature, as well as a specific heat capacity, which we represent usually with C. Let me check. Okay. So if we put out that whole calculation, I could say my 2.5 grams times 0.372 times the temperature change, which is 4.9, gives 4.6 joules. I will say, generally, you will always use Kelvin for temperature calculations, except in a case of change in temperature. You can use Kelvin or Celsius. Remember, they're on the same scale. Raising something by 1 degree Celsius also raises it by 1 Kelvin. And so the change in temperature numerically will be the same. All right, that kind of brings us to the end of this chapter's slides. I know that's ending a bit abruptly. I am going to do more of that practice in class with you. I want you guys to, I'll include a few problems for you to try with this. So, all right, have a good one.